You guys hear me okay? Okay. All right. Do you guys have any questions over what we were doing last time? So chi-square goodness of fit tests seem logical to you in terms of why you set up the expected values the way that you set up the expected values? Okay then. So I had mentioned last time. Let me do some screen sharing. I had mentioned last time that there are 3 different types of chi-square tests. There's a chi-square goodness of fit test, which is basically what we were doing yesterday, and in the case, or on Wednesday rather, and in the case of a lot of the goodness of fit tests, well, let's see, I'm having some navigating difficulties. Give me just a minute. In some cases, we're testing the goodness of fit of a set of data to a theoretical distribution. And so as we saw in the genetic data, when you do genetics, there's a set ratio that you expect certain phenotypes to occur in, a 3-to-1 ratio. 3/4 of the population would be round, 1/4 of the population would be wrinkled. And that's based on kind of the theory of how we know genes get inherited by organisms. And so we don't rely on any other data other than just this kind of theoretical expectation to set up our expected values. But then when we looked at the prison data, the incarceration data, we used the population of human beings to basically set up the expected values for what you might expect to find in the incarcerated data. And so in that case, we used one set of data to set up the expectations, the expected values of the other data, and then tested the observed data against those expected data. And so when we were talking about these different types of tests, you might also remember that I told you the main way in which these tests differ from one another is how you go about setting up the expected values. In a goodness of fit situation, you either use some theoretical expectation or some actual distribution that you want to compare your distribution to see how well those two distributions fit with one another. Chi-square test of homogeneity basically tests to see if all the frequencies are the same. And so once again, in this case, we're going to be setting up the expected frequencies on the basis of what the expectation would be if all the categories had an equal representation of all the individuals in the study. And so that's what we're going to do next. This is some data from the 2016 primaries. And so these are data from a public opinion poll basically taken relatively early on in the election. Wait, 2016? Yeah, 2016. No, because Biden wasn't even in that. When was this? When did I get these data from? Andrew Yang. Oh yeah, no, I guess this was early on in the 2016. The 2020 primaries. So yeah, this would have been fall of last year that I put these data together. So this was a public opinion poll looking at Democratic candidates early on in the primary races. Biden, I don't even think at this point had officially even started running for president. And so what we saw early on was Pete Buttigieg and Bernie Sanders seem like they're ahead of everybody else in terms of support. This was a survey of 2,147 people, and this is how the different people expressed their potential to vote in the upcoming Democratic primaries. And so we can take this as the observed. And one of the things that pollsters might want to know is there any sort of preference among Democratic voters in terms of the number of individuals who are supporting different candidates? And so the alternative hypothesis is that there is a preference. And this alternative hypothesis is set against the null hypothesis of there is no preference. And so what we would do, since we have 1, 2, 3, 4, 5, 6, 7, since we have 7 candidates, what we would simply do is divide the total number of individuals, 2,147, by 7. So let me get my calculator. 2,147 divided by 7, that's 306.7. And that then becomes the expected value, because the null hypothesis here is the expectation that all of these candidates are preferred equally. And then the chi-square test is calculated the same way we've done it before. Chi-square is simply the sum of the observed minus the expected squared divided by the expected. And so it's the same equation, except now only rather than doing this over 3 categories, we're now doing this over 7 categories. So it's a little more math, but it's the same math. And so the observed minus expected squared divided by expecteds are here. When we sum all of those up, we would get a chi-square value that is 1,016.5. 0.57. And once again, this is an extremely large chi-square statistic. Go to Moodle really quickly with me. So I'm going to go to Moodle. I have my applied stats class up there. You'll see that I've added a thing up here at the very top is this kind of general category before we start getting into weekly stuff. And in this general stuff, I've given you some our cheat sheets. The syllabus is there, the schedule is there, the YouTube link is there. But I've also added a folder called tables, statistical tables. And in these statistical tables, I've put 2 tables in there so far. One of these is the critical values of the chi-square statistic. So download that and open it up really quickly. And I will do the same. So this is a chi-square table. So we've downloaded tables similar to this in class to look at really quickly. Most statisticians have a book like this. This is a table. This is a book of statistical tables. It is just full of tables of statistics of various types. It's just lots of numbers on pages. And this is the chi-square table. And let's blow this up a little bit. So we would normally be testing things at the 0.05 level here. That's the 95% confidence level. And this just basically shows you the critical values for the chi-square test. But what I want you to do is I want you to pay attention to, let's blow this up so we can see it. Pay attention to this column, the 0.05 column. The V over here on the side is the degrees of freedom. And so for this test that we just did, we would want to look up the chi-square value for alpha of 0.05 and 6 degrees of freedom, because we have seven categories that we're looking at, 7 candidates that we're looking at. And when we do that, we see that the chi-square value for an alpha level of 0.05 and 6 degrees of freedom is 12.592. And so what this is basically telling us is we have to observe a chi-square value of 12.592 or greater in order to say that this distribution differs from the expectation of a uniform distribution and an even distribution. And what you'll notice about this table is as you get to higher and higher degrees of freedom, the numbers get bigger and bigger. The threshold that you have to cross gets bigger and bigger until you're down here at 100. If you're comparing 101 categories, so you have 100 degrees of freedom, you would have to have a chi-square value at the 0.05 level of roughly 124. Well, the reason that these numbers get bigger is that the more categories you have, the more things get added up. And so you would expect that you would need a larger and larger chi-square value in order to detect a difference because you're summing up across all of the categories. And so the more categories you have, the bigger the chi-square value gets. And so that should kind of make intuitive sense to you. As you can see for this particular test, the value that we generated, 1016, is way, 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 way bigger than the chi-square value that is in the table, which means that there is a preference. And so we can go back to the PowerPoint and we can look at these numbers. And it should be apparent to anybody looking that obviously people at this particular stage in the primary season were preferring Pete Buttigieg and Bernie Sanders to, for example, Andrew Yang and Tom Steyer. The numbers are radically different. And when you look at what the contribution is to the overall formation of the chi-square, it's driven by big chi-square contributions from Buttigieg and Sanders and big contributions to the chi-square of Andrew Yang and Tom Steyer. These intermediate candidates, Elizabeth Warren, Joe Biden, and Amy Klobuchar, are all kind of clustered here in between, and they're all relatively close to the expected value, so they're not really contributing very much to the chi-square value overall, and as a result, it's just the preference for Biden and the avoidance, the preference for Buttigieg and Sanders and the avoidance of Yang and Steyer, which is driving this really big chi-square value. Now, Warren was also contributing a little more than, for example, Biden and Klobuchar at this point, but it really is being driven primarily by the Buttigieg-Sanders versus Yang and Steyer differences. And you could apply these kinds of methods to any kind of statistical polling that a pollster would do, either about political candidates or about political issues or whatever you would want to look at. And so this is a test of homogeneity. You can also do a thing called a G-test. So a G-test is just another version of doing this sort of thing that I want you to be aware of. G-tests tend to be a little more advantageous when you have frequencies that are close to zero. So for example, down here with Tom Steyer, it gives you a similar sort of equation. In this case, you take the observed value and you multiply it times the natural log of the observed divided by the expected. And when you get that, it gives you a larger number, but they're still both amazingly large. And you evaluate this the same way that you would evaluate the chi-square test. You look this value up in the table for, once again, 6 degrees of freedom, and you evaluate it just as if it was a chi-square statistic. So whether you use the chi-square statistic or whether you use a G-test, it doesn't really matter in most cases. They're going to give you a qualitatively similar decision at the end. All right, chi-square tests about homogeneity. Any questions about those? Okay, then. The last test that we're going to look at is a chi-square test of independence. And this happens when we have what's called cross-classified frequencies, and we want to know if they're independent of one another. And so what a cross-classification frequency table looks like is it looks like this. These are data from, I don't remember where this example comes from, but basically we have two things here that this biologist was interested in. He was interested in the dispersal mechanism for seeds of plants, and then whether or not, and you have seeds that can be dispersed by ants and by vertebrates, and then do they regenerate themselves either by seeds or can they reproduce vegetatively by sending off offshoots that then sprout up a new plant. And so they were interested in whether or not the method of regeneration was independent from the method of dispersal. You know, are ant dispersed seeds primarily going to be seed only, or are ant dispersed seeds equally both seed only and vegetative? Do vertebrate distributed seeds, do they produce mainly by seed only, or do they produce more vegetatively? And so the test that is being asked is there an association between the dispersal mechanism and the regeneration mechanism, or are these two things independent of one another? Because this cell here, the ant seed only cell, is influenced by seed only across ants and vertebrates, and is also influenced by ants across regeneration type, the way you calculate the expected frequencies for this type of test is different. So in this case, the expected frequency is equal to the row total times the column total divided by the total. So to figure out what the expected frequency is of ants and seed only, we would take the seed only row times the ant column divided by 88, which is the total. Oops. So let's do that. Actually, I'm gonna shift methods on you here. Let's go to my screen. Give me a minute to make the transition, because chances are all right, can you guys see my blank screen? Yep, okay. So what we have here is we have ant dispersal versus vertebrate dispersal. We have regeneration by seeds or vegetative regeneration. And we have 25 species in this category, 6 species in this category, 36 here, and 21 here. That gives us a total of 61, total of 27. And along the columns, we have a total of 31, and we have a column of 57. And then the grand total there is 88 different species of plants. And so this is the observed matrix. So we can calculate the expected for, once again, ant versus seed by basically taking the seed regeneration total, 31, times the ant column, which is 61, divided by 88. And let me pull up a calculator on my computer really quickly here. So 31 times 61 is 1891 divided by 88. That's 21.49. So this would be then 21.49. We would do the same thing for vertebrate dispersed seeds that are seed regenerated, which would be 31 times 27 divided by 88. 31 times 27 divided by 88, which equals 9.511. And then we would take for vegetative regeneration and dispersal would be 57 times 61. 57 times 61 divided by 88, which would be 39.51. Are you guys working? I've had to turn you off so I can actually see my screen. You guys working along with me? Yep, okay, good. And then the last one would be vegetative regeneration by vertebrate dispersal, which would be 57 times 27 divided by 88. 57 times 27. Whoop, that's all right. 57 times 27 divided by 88 equals 17.489. So if we add all these up, so we take 21.49 plus 9.511 plus 39.51 plus 17.489. That should all equal 88. So that sums to 88. So remember, in all of these calculations, you can always double check your figures by basically making sure that the expected values add up to the same total that the observed values add up to. So now at this point, all we have to do at this particular juncture is we need to calculate what the chi-square value is. Well, the chi-square value is just going to be the same way we've always done it. It's just the observed 25 minus 21.49 squared divided by 21.49 plus 6 minus 9.511 squared divided by 9.511 plus 36 minus 39.51 squared divided by 39.51 plus 21 minus 17.489 divided by divided by not 9.51 divided by 17.489, and this is squared also. So we could do this by hand on our paper. We could also just go into Excel and do this as well, and maybe do it a little faster. So I'm going to just open up an Excel file really quickly. And when I open up an Excel file, I'm actually just going to make myself two little matrices here, one of which is 25. Well, actually, 25, 36, 6, and 21. And so 21.49, 39.51, 9.511, 17.489, And then I'm just going to put in the equation equals to those, that minus that squared divided by the expected. And then I can copy all of those over and I can sum them. And so I arrived at a chi-square value of 2.886. Is this what you guys found? Or are you still calculating? Okay, Blaine, that's what you got? Okay, good. Let's let everybody else get caught up. Give me some indication, a thumbs up or hands up or something when you've finished and you got the answer that I got. So what I did when I did it is I just put in the values, 25, 36, 6, and 21, and then put in the expected values. And then in Excel, it's easy enough to just write an equation that basically takes the observed minus the expected, squares it, and then divides it by the expected. And then when you do that, you can actually just copy that formula across quick and easy, and then get it to sum it across those columns, and it will give you the value. So these types of equations are just really easy to work by hand. They're even easier to work out in an Excel spreadsheet. So everybody got 2.88? Or Samuel, are you still working? No, you got it. Okay. All right. So now we need to know, is this value, this value that we observed, so we have a chi-square value of 2.88, what did I say? 6. We're going to evaluate this at an alpha level of 0.05, but now we need to know, how do we calculate the degrees of freedom? The degrees of freedom in this situation are the number of rows minus 1 multiplied times the number of columns minus 1. And in this case, because we have 2 columns and 2 rows, it ends up being 1 times 1. So our degrees of freedom in this case is 1. So when we go to the critical table, the table of critical values for chi-square, we need to go to 0.05, and we need to look at the table value at 1 degree of freedom. And we see that the chi-square from the table at 0.05 and 1 degree of freedom is actually 3.841. And so because our observed value is less than 3.841, we would conclude that there is no, we would conclude that these things are independent. Independent of one another. So the mode of dispersal by vertebrates or ants essentially doesn't have anything to do with the method of regeneration. That's what these data are saying. And it kind of makes sense, because when we looked at the observed value and the expected value, they're not that far from one another. Observed value not that far from expected. Observed not that far from expected. Observed not that far from expected. As a result, the chi-square doesn't get very big, and it doesn't get big enough that it surpasses the rejection value that we use to reject the hypothesis of independence, to say that they're not independent of one another, that they're actually related to one another. Okay? So chi-square tests of independence, I think, are the ones that students have the most trouble with. And the reason is that the way you calculate expected values is different from the way you've done them in the previous two examples. But think about it from a conceptual standpoint. Ant dispersal and seed-only regeneration is influenced by how many plants are seed-only in terms of their regeneration, and how many plants are dispersed by ants only, as opposed to by vertebrates. And so it makes sense that the row total times the column total would be the things that you're interested in determining what the dispersal mechanism, or what the expected value is for this category. But then you have to scale that by how many observations you have total. Let's go to a more complicated example. And because this is more complicated, it would take us a really long time to work through this in class. So this is basically looking at emergency room visits. So we have a questionnaire which basically says, have you visited the hospital in the last 6 months? Have you visited the hospital in the last 7 to 12 months? Or has it been more than a year since you've visited the hospital? And then it looks at income. Do you make less than $3,000 a year, $3,000 to $5,000 a year, $5,000 to $7,000, $7,000 to $9,000, or $7,000 to $10,000, and then $10,000 or more? And then it just has responses to this table. Well, it looks like a lot more people have visited the hospital in the last 6 months than in 7 to 12 months or greater than a year. And it also looks like people who have more money tend to visit the hospital more than people who have less money. So it stands to reason that the expected value should vary somewhat depending upon the frequency at which you go and what your income is. And so we would calculate the expected values the same way we did in the last time. We would basically, to calculate the expected values here for 6 months, less than $3,000, we would multiply 259 times 1640, divide that by 2764, which should give us 153.68. For this one here, 6 months and $3,000 to $4,999, we would take 326 times 1640 and divide it by 2764, which would give us 193.43. And we would continue doing this for the whole table, and we would get these values. So the black values are the observed values, the red values are the expected values. And then to calculate the chi-square for this, we would simply take the observed minus the expected, square that, divide it by the expected, add that to the observed minus the expected, square that, divide that by the expected for all of these things. In this case, we have 3 columns and 1, 2, 3, 4, 5 rows. So the degrees of freedom would be 5 minus 1 times 3 minus 1. Number of rows minus 1, number of columns minus 1. So this would be 4 times 2. So this would be evaluated at 8 degrees of freedom. And I forget if I have, no, I don't have on the next thing here. So let's take this data, and once again, let's go and build ourselves an Excel file where we can do this. So let me get out of this really quick. So you're going to get a homework assignment from me dealing with chi-square values. I should send it out later on today. And when you do this homework assignment, you can either do it you'll do it by hand in some cases, and you will also do it, it might be easier to do it via Excel spreadsheet in some cases. So let's just take this less than 6 months, 7 to 12 months, and greater than 1 year. And we're going to basically have less than 3,000, to 4,999, 5,000 to 6,999, and 7,000 to 9,999, and then greater than 10,000. And so what we have here at the beginning is we have 186, 227, 219, 355, 653. We have 38, 54, 78, 112, 285. And we have 35, 45, 78, 140, and 259. Are you guys doing this also as I go through it? You should, just to get a feel. So the first thing that we need is we need the sums of the rows. So you can just use the sum symbol up here to give you that, and then drag that down. It should give you 259, 326, 375, and 607. You can use that same symbol to give you the column totals, 1640, 567, and 557. And then, oh, I missed one of these. 1197, that one there. And then all you have to do is either sum the columns or sum the rows. It doesn't really matter, but it should give you 2764. Since that was summing across the rows, we can once again check our values and do sum across columns, and it should give us the same answer because we should never trust computers. Okay, so that gives us our raw data and our row totals and our column totals. So this basically is the observed values. And so what we have to do next is we have to calculate the expected. And expected is, once again, for this category here, it's just going to be equal to the row times the column divided by 2764. And because it's going to be 2764 every time, we can just do 2764. In this case, it's going to once again be equal to the row times the column divided by 2764 again. So for this row, we can actually make this a little simpler if we just go up here. And since the column reference is going to always be the same, we can make this, we can put a $sign out here in front of the B and a $sign in front of the 14. And when we do that, if we just drag down now all of the rows, it should just automatically calculate that for us. Same thing here, if we do, in this case, row times column, but then we're going to make this column a fixed reference by putting a $sign in front of it, in front of the C, and a $sign in front of the 14. And then once again, divide that by 2764. I forgot a division sign. That is not a time sign, that is a division. We can sum across that. We can do the same thing for the last column. The last column is equal to, once again, the row times helps if you do the right column head. And once again, we're going to make that a fixed reference, and we're going to divide by 2764. And once again, we can take that whole thing and copy that. So now we should have a set of values here that I'll just shade in yellow. Oh, I didn't want to change that. I will shade these things in yellow, and I will shade these things in like light blue. And they should be the same dimensions, 3 columns wide by 5 columns, three columns wide by 4 rows deep. And if you go and highlight all of that, it'll give you the sum of that value down here, and it should sum to 2764, just like the sum over here is 2764. So you could actually do a sum equals sum, and you could actually put that in here, but you don't actually need to, because if you just highlight it with your cursor and look down here, it tells you there are 15 values. The average is 184.266, and the sum is 2764. So it shows you these summary values down here. So now that you've got the expected values, what do you need to do? We need to calculate the chi-square value, right? So you need to open up 2 parentheses, take the observed minus the expected, raise that to the second power, the power of 2, and then close off that parentheses, and then divide that by the expected. And that gives you the contribution of the chi-square of this part of the table. But now, because these are all relative values, relative references, if you grab this thing in the right-hand corner and pull it over, it will autofill such that this one is the observed minus the expected, once again divided by the expected, squared and then divided by the expected. And so once you have that done, you can then just take all those 3 and drag them down 1, 2, 3, 4. That's 1, 2, 3, 4, 5. And now you have this one corresponds to this cell times that cell squared divided by that cell. And so you can very quickly and easily calculate then what the total chi-square is by taking this thing and pasting it down here, because you will see that this is now the sum of everything in that box. So chi-square tests are really easy to calculate. So this is now the observed chi-square value for this test of independence. And now what we need to do is we need to find out, well, what's the table's value? Well, in this case, we have 8 degrees of freedom. So we would go to 0.05, and we would go down to 8 degrees of freedom, and we would find that the table's value is 15.507. Actually, I should have said tables, not tables. The critical value of the chi-square is 15.507. And in this case, the observed chi-square value is way bigger than the critical value. So we would say in this case, there is some lack of independence here. Well, where is that lack of independence coming from? Well, we can look down here at the chi-square table and say, well, what things are contributing to this chi-square value being big? Well, it's not these small values here. We'll just code those as red. It's not this small value here. It's due primarily to things like this area here and these areas here. Those correspond. We can take this whole thing, and actually high values here as well. Well, and for that matter, kind of high values here and here. So we can take these things now. So I'm just going to highlight these. I'm going to copy, and I'm going to paste those color codings over here, and I'm going to use paste special, and I'm just going to paste formatting. So we're, oh, no, never mind. Don't do that. Well, I'll just do it this way. So we coded these things green, we coded these things green, and we coded that green, we coded these things and that as red, meaning that they don't really contribute very much. So basically, what's contributing a lot to this chi-square value being big is, in this case, poor people. Go to the hospital less frequency. People with more money go to the, so sorry, these guys are going to, sorry, poor people are going to the hospital more frequently than expected, and wealthy people are going to the hospital less frequently than expected, because of these things are all below the expected, or sorry, are all above the expected values, and this one is below the expected value in the 6-month category. And then when we look at really long periods of time not going to the hospital, poor people are in this category way less than you would expect them to be, and wealthy people are also less than you would expect them to be, but they're more in this intermediate category. So wealthy people go more in this is 7 to 12 month period. And once again, in this intermediate period, it looks like poor people are going to the hospital less than you would expect it. So poor people go very frequently. They go less in this intermediate period, and they go less in the long period. And that might just be because poor people might have more health issues, and as a result, they have to go to the hospital more often than wealthier people who have probably better health care, better health overall. They tend to go less frequently, and as a result, they tend to be more represented in the infrequent visits to the hospital. And once again, those are all borne out by what portions of the chi-square table are leading to this really big chi-square value. And so you can decompose what the contributions are to the chi-square. So one of the ways that you can do this, and I was actually just helping a scientist friend of mine do this. She was dealing with some genetic data that she was doing these types of analyses with. And you can basically ask yourself, of the total, what is the percentage contribution of this particular value, 47.8923399, and then we can multiply that whole thing times 100. And so you can calculate the percentage contribution of each of these things to the total. This thing should then sum to 100 if we've done our math correctly. Yep, it sums to 100. So some of these things are contributing, more than 10% to the total chi-square value, some of these categories are contributing hardly anything to the chi-square analysis. And because of that, because these things aren't all uniformly low, there's some interaction between how frequently you go to the hospital and what your income level is. And that's what the test of independence is asking, is the frequency of visits related to, or is it independent from, the income that you have? If it isn't, then all of these things would be roughly the same size and they would be all relatively small in terms of their percentage contributions to the total. So percentage contributions would be relatively even and relatively small, leading to a small chi-square value, which would lead you to conclude that these things are independent. But because you have pattern to these proportions that they're contributing to the chi-square, where some things are really small and other aspects of the table are really large, then that's what's driving this thing towards a person concluding that frequency of hospital visits is dependent upon one's income. And that's what the test of independence is actually trying to get at. Questions about this? Do you feel confident that you could perform the 3 types of chi-square tests? Do you feel better about working them out by hand, or do you feel better working them out in an Excel spreadsheet? That's not a yes or no question.
Excel.
Okay, why Excel? Who's that, Champ?
Yeah, I feel like there's less room for error, personal error.
Okay, yeah. So one of the reasons that I oftentimes will do this in Excel is, one, it's quicker in many ways because you're not plunking everything out on the calculator, and also because you're not plunking it all out on the calculator, you're going to be less likely to make keystroke errors. And so you'll oftentimes see me doing this kind of thing to work out chi-square statistics. On your homework, if you do it this way, I just want you to present to me what your calculations were, whether those are handwritten calculations or whether you reverted to Excel to do those. The weird thing about R, and the reason that we're not going to be doing this in R, is that R is really terrible at really simple statistics like this. You can get it to do it, but you have to give it a lot of information in order to do it. And oftentimes it's just as quick to generate that information by yourself and then just finish the calculations yourself as it is to generate that information and feed that into R. If you're interested in how this is done in R, I can certainly show you how to do chi-square tests in R. But things like R, I generally like because they save you a lot of time and effort. And my experience with chi-square analyses is that R doesn't really save you much at all in terms of time and effort. So that's why, especially for relatively simple data sets, I just go with simpler methods because R is kind of like over-equipped. It's like driving a Lamborghini to the grocery store. It's just really way more horsepower than you need for the task at hand. And as a result, it doesn't really do very well at it. It's cumbersome in the same way that you can't put a lot of groceries in the back seat of a Lamborghini. So I've heard. I've never actually been even near a Lamborghini. All right, questions?
Can you just click on one of the boxes that aren't highlighted so I can see the formula again?
Yeah, one of these?
Yeah.
Yep. So for this, you don't have to do this. This is just one way of thinking about the degree to which this part here, this cell here, contributes to the overall chi-square value. So do you want these percentages? So this is, I can do this, hold on. So in the same way that you annotate R scripts, you should also probably annotate any Excel files that you're working on. So which ones do you want me to click on? Do you want me to click on expected, chi-square calculation, or percent contribution?
Percent contribution.
Okay, all right. Let me correct my spelling mistake. Yeah, so in this case, it's just this value here divided by the total, which was 47.89. And I just put that in there because it's just as easy to put the number in there as it is to make a static cell reference. We could have done this just as easily. Instead of typing in 47.892399, we could have just as easily clicked on that value there and then made it a static reference by putting a $ before the J and a $ before the 22. And it does the same thing. And once again, when we copy that across all of the cells, it gives us the same value. It's just that now, rather than having a number in that category, it just has a static cell reference. Does that get you what you wanted? One of the reasons that you will see me using static cell references rather than numbers is because if I then have a 3x5 chi-square value or chi-square test that I need to run, I can change this from this to category. Whoop, what happened? Category A, category B, category C, row D, E, F, G, and H, and I. And then I can change these values. I can change my raw data to 246, 587, 224. And as I do this, it basically updates everything it updates all the calculations simultaneously. And I'm not sure why that did that. Oh, that's weird. It updates all the calculations simultaneously. So you could actually take, let's go back and undo all of this since we did all of this for a particular example. So you could actually take this whole thing copy it to another sheet, and then just go, I don't know why that one is not behaving correctly. I don't know what that is doing. Anyway, in theory, you should be able to just oh yeah, something happened to our cell references. You should be able to just copy that thing and then change the numbers, and it should just automatically auto update. But clearly something went wrong with this situation here. I'm not sure why. Yeah, something went wrong with that copying thing. But anyway, the nice thing about having gone through this work, it's then just updatable. And you can also just use this, and if you only have 4 rows and 3 columns, you can just get rid of a row And once again, it should retain all of the calculations once again for you. So in that way, Excel is pretty flexible about things. I'm not sure why this didn't work, copying it to another sheet, but in that way, it's kind of like in R, once you have a script that works, you can just go in and tweak the things in a script to get it to do another job for you, just by changing data frames, changing variables, and things like that. All right, other questions? All right, what we have in store, yeah, go ahead.
Can you go back over expected real quick? I have the wrong number, so I want to double check where I went wrong.
Yeah, so expected is simply well, let's just do it for this one. It's the row total times the column total, in this case, divided by 2764. And once again, we could put in 2764, or we could just put in the cell reference. But when we put in that cell reference, we're going to want to make that cell reference a static cell reference rather than one that fluctuates. So here it's $E, $14, versus here it's 2764. Both should give you the same answer. And anytime you want to see what a formula is referring to, if you click up here in the formula bar, let's see if I can, it's possible to make that formula bar bigger. And it is not. I don't know how to make that formula bar bigger. But when you click in it up here, it will highlight in different colors what cells you're referring to. So in this case, the bluish cell is E9. That's the row total. The red cell is B14. And then the purple cell is E14. And so it'll show you in here what cells you're actually referencing to down in your spreadsheet. Blaine, did that get it for you?
Yeah, I had a plus sign instead of a multiplication sign. That was just me.
Oh, yeah. Okay. Yeah. Simple thing. So we don't really have time to start on testing normality. So here's what we have to do next week. Next week, we need to talk about normality on Monday, and then we're going to talk about t-tests on Wednesday and Friday. And so I want to point you to things in the book that you should read before then. Well, now I'm looking for it in the book, and I don't really find it in the book. So in chapter 2, at the beginning, when it's talking about normality of distributions and the normality assumption, so read, if you haven't already read it, read page 14 to page 22, the end of the section that ends on page 22 and 23. So up to the beginning of section 2.4. That it revisits some things that we've already talked about, things like normality and what 95% confidence intervals have to do with things like this. It doesn't actually take you through how to calculate whether or not a distribution is normal. That's kind of an involved process. We're going to work one example in class by hand, and you're going to work one example on your homework by hand, and then we're never going to work normality problems by hand again, because they're a total pain in the butt to do by hand. And you need a statistical table in order to do it. And then the next thing that I want you to read is the beginning of chapter 3. So this would be page 32 up through the beginning of section 3.2, which is on type 1 and type 2 errors. This takes you through t-tests, which are the simplest of all possible hypothesis tests for testing means. And so that'll be useful for really Monday, Wednesday, and Friday. I guess it'll take us a good chunk of the time on Monday to get through normality testing, but then doing t-testing is actually pretty quick and easy. So that's what we have for next week. And then on March 1st, so this is in the schedule, you will recall that there is one exam. So if you go and look at the syllabus and you look at the graded assignments, there is one exam. That exam is on March 1st if you look at the schedule. So let me pull up the schedule. Okay, I pulled up the schedule. Why did it not open? Well, that's just weird. It's not lurking somewhere, is it? All right. I don't know why. Okay, I can't seem to get the schedule to open on my own computer, which seems just incredibly stupid. Anyway, it's on the schedule for March 1st, if I'm recalling correctly, and I just need to go in and get a copy of the schedule. The schedule is on the Moodle site. But anyway, that's the first exam, and it's going to cover everything that we covered up through the end of the week next week. So it should cover general ideas about central limit theorem, populations, the relationship between populations and samples. I sent you your homework overnight yesterday afternoon. Many of you could have a better working definition of what a statistical population is, and I made notes about that on your papers as well. So we can talk more about the test next week. That's the only test for the semester. Everything after that is problem sets to practice techniques by hand, and then reports on larger data sets that you have to work through R. And then that's what we'll be doing the rest of the semester, learning a technique, working it by hand, working it on the computer, and then doing a report. And then that same thing just over and over again for different techniques. All right, I will see you guys on Monday. Read the sections of the textbook dealing with normality and dealing with t-tests. All right.